On April 26th, 2026, at 4:23 in the morning UTC, the ground moved in western Mongolia. Magnitude 5.9, 10 kilometers deep. The third shallow quake in 24 hours along a fault network that ripped open the planet in 1905 and again in 1957. It has been quiet for 121 years. Stay with me, because by the time we're done, you'll understand exactly why this is the most dangerous fault you've never heard of. Before we get into it, if you are new here, hit like and subscribe to The Quiet Archivist. Because we are tracking every piece of this, the cluster the headlines ignored overnight. The fault system most hazard maps still treat as separate pieces. The magnitude 8 earthquakes 1905 buried in public memory, and the 1,500-kilometer network that has been quietly loading itself for 121 years while almost nobody watches. If something is actually stirring on this system, you will want to be here when it happens. Now settle in and let's get into it. At 4:23 in the morning, Coordinated Universal Time, on April 26, 2026, the ground moved in western Mongolia. The United States Geological Survey logged it as a magnitude 5.9. The European Mediterranean Seismological Center logged it as a 5.8. That small disagreement is normal. Different sensors, different math, different calibration networks. What matters is that something snapped roughly 10 kilometers below the surface, in a part of the world almost no one outside specialist seismology has ever heard of, about 168 kilometers southeast of a town called Kovd. The official damage assessment came back almost immediately. Pager, the automated impact system, lit up green. Minimal expected damage. No major casualties anticipated. The kind of earthquake that, on any normal day, would barely register as a footnote in a regional bulletin. And on the surface, that's exactly what it was. A green alert quake in a sparsely populated stretch of Central Asia. But here's the thing. It wasn't alone. In the 24 hours leading up to that moment, two other shallow earthquakes had rattled the same broad band of crust. A magnitude 4.8 in southern Siberia on April 25th. A magnitude 4.7 in the Tuva region, also on the 25th. All three of them shallow. All three of them 10 kilometers deep or less. All three sitting along the same enormous tectonic corridor stretching across Mongolia, Siberia, and northern China. Now, before you start picturing dominoes falling, I have to be honest with you. The Earth produces somewhere between 500 and 700 magnitude 5+ earthquakes every single year. Statistically, 3 quakes in 24 hours across a region this large is not unusual. It's not even particularly interesting. The distances between these events, anywhere from 400 to 550 kilometers, are far too great for one quake to mechanically trigger another in the conventional sense. So why are we even talking about this? Because all three of them sit on the Bolnay-Khangai-Sayan fault system. And that name, as obscure as it sounds, is one of the most quietly significant in the entire science of earthquake geology. This system has produced magnitude 8 earthquakes. Plural. It has ripped open the earth in ways that would make the San Andreas blush. And it has been almost completely ignored by the public, by the media, and in many ways by global hazard planning. So this isn't about what happened on April 26th. This is about where it happened, and what that place has done before. To understand why 3 small quakes in a remote corner of Asia are worth pausing on, you have to stop thinking about faults the way most people picture them. When you hear the word fault, you probably imagine a single crack, a line on a map, the San Andreas zigzagging up California. One fracture, one story. The Bolnay-Khangai-Sayan system isn't like that. It isn't a fault, it's a network. A continuous belt of deformation stretching roughly 1,500 kilometers across Mongolia, southern Siberia, and the edges of northern China. Imagine drawing a jagged line from the western steppes through the Khangai Mountains and up into the Sayan Ranges, and you start to get a sense of the scale we're dealing with. These aren't random, unrelated cracks. They're interconnected strike-slip structures, meaning the crust on one side slides horizontally past the crust on the other. And because they're linked, the same stress field that loads one segment can quietly load segments hundreds of kilometers away. Geologists sometimes describe this as the difference between thinking of a fault as a single fuse and thinking of it as a wired electrical grid. When you flip a switch in one part of the grid, lights flicker somewhere else. The engine driving all of this sits thousands of kilometers to the south. The Indian tectonic plate has been ramming into Eurasia for roughly 50 million years, and that collision is what built the Himalayas. But here's the part most people don't realize. The Indian plate didn't just shove things upward, it also squeezed the crust to the north and east, and that squeezed crust had to go somewhere. It had to escape sideways. Geologists call this continental escape tectonics. Picture squeezing a watermelon seed between your fingers. It doesn't crush, it shoots out. Mongolia and parts of Siberia are essentially crustal watermelon seeds, getting shoved sideways by the slow-motion fury of India crashing into Asia. The Bolnay-Khangai-Sayan system is one of the primary release valves for that pressure, and this is where most public hazard maps fall short. They tend to treat faults as isolated lines, assigning each one its own probability and its own potential magnitude. But history shows that great ruptures in this region don't politely respect those boundaries. They jump across segments. They link up. They behave as one organism rather than a row of individuals. The last time this system spoke as a single connected entity, it didn't stop at one earthquake. It produced two. And the second one was so large, so violent, so geometrically improbable, that scientists are still arguing about it more than a century later. Let me ask you a question. When was the last time you heard someone bring up the 1905 Bolnay earthquake at a dinner party? Or in a documentary? Or in a news article about earthquake risk? Probably never. Now ask yourself the same question about the 1906 San Francisco earthquake. You've almost certainly heard of that one. It's in textbooks. It's in films. It's in the cultural memory of an entire country. The two events were comparable in raw seismic scale. Both involved enormous strike-slip ruptures along major continental fault systems. Both released energy on a planet-shaking level. So, why does one of them live in our collective imagination, while the other might as well have happened on a different planet? The answer is something I'm going to call seismic visibility bias. An earthquake doesn't enter public memory because of its size. It enters public memory because of its consequences: population density, infrastructure damage, economic loss, photographs, survivors who can tell the story to journalists who can tell it to the world. San Francisco in 1906 had all of those things: a booming city, brick buildings, fires that consumed entire neighborhoods, photographers with cameras, newspapers with telegraphs. The disaster turned into a global event before the dust had even settled. Mongolia in 1905 had almost none of those things. The region was sparsely populated. Many of the people living there were nomadic herders living in gurs, the round felt-walled structures often called yurts in the West. And here's the quietly fascinating part. Gurs are remarkably earthquake-resistant. They flex. They sway. They don't crush the people inside them when the ground shakes. So even when a magnitude 8 rupture tore through the steppe, the human casualty count stayed astonishingly low for the size of the event. Low casualties meant low news coverage. Low news coverage meant low global attention. And low global attention, decade after decade, meant that one of the largest continental earthquakes in modern recorded history quietly slipped out of public consciousness. This is the irony at the center of how we remember earthquakes. The biggest events sometimes happen in places where there's almost no one to witness them, and so we forget that they ever occurred. Which means our intuitive sense of where the most dangerous faults are tends to be wildly skewed toward the ones that have already hurt cities. It's a kind of survivorship bias in reverse. Some of the most powerful fault systems on Earth are not the famous ones. They're the ones nobody is paying attention to. And in 1905, this particular fault system produced something on the scale of San Francisco, and almost nobody alive today remembers it. So we come back to those three little quakes on April 25th and 26th, 2026, a 4.7, a 4.8, and a 5.9, all shallow, all on the same enormous fault system. The question isn't whether they were unusual. The question is what, if anything, they actually mean. There are essentially three ways to read this signal, and I want to walk you through all of them honestly, because too often these stories collapse into either total dismissal or total panic, and the truth almost always lives somewhere stranger and more uncertain in between. The first reading is the conservative one. This is just background noise. The Earth is constantly fidgeting. Earthquake occurrence in any given region tends to follow what's called a Poisson distribution, which is a statistical pattern where events appear randomly clustered even when they're independent. 3 quakes in a day in a 1,500-kilometer-long fault network has essentially no predictive value. Nothing to see here. Move along. The second reading is the intermediate one. This cluster represents normal stress redistribution within an active fault network. The crust in this region is constantly under load, and small ruptures are the system's way of releasing tiny amounts of accumulated strain. It's not a warning. It's just the network doing what it has always done, breathing in and out at a scale we can barely perceive. The third reading is the speculative one. This is the reading that makes seismologists nervous, because it walks the line between pattern recognition and pattern projection. In this view, the cluster could represent the very earliest hints of system-wide reactivation, not a prediction, not an imminent threat. Just a faint flicker that might, if you squint hard enough, resemble the kind of low-level seismicity that has sometimes preceded larger events on other fault systems around the world. Let me be absolutely clear about something. There is no scientific basis for claiming that a magnitude 8 earthquake is about to happen on this system. A single magnitude, 5.9, releases roughly 1/30,000th of the energy of a magnitude 8. They're not even in the same league. The math doesn't work. The physics doesn't support it. But fault systems don't usually announce themselves with neon signs. They don't politely send a memo before they go. They speak quietly, in vibrations and offsets and patterns that are easier to recognize in hindsight than in real time. To understand what this signal might or might not mean, you have to go back to the last time this fault system spoke loudly, not in whispers, in a roar that bent the surface of the Earth. The story begins in the summer of 1905 on July 9th in the Tsetserleg region of central Mongolia. The exact local time is debated because of poor timekeeping in the area at the time, but what's not debated is what the ground did. A massive section of crust ruptured, releasing a magnitude estimated at right around 8.0. The surface break stretched approximately 190 kilometers, with additional rupture continuing below the surface that paleoseismologists have only been able to map decades later through trenching and remote sensing. The motion was primarily strike-slip, with a significant reverse component, meaning the crust didn't just slide horizontally, it also crunched upward in places. Horizontal offsets reached roughly 2 to 3 meters in a single instant. Imagine the entire side of a hill abruptly jumping the length of a car, sideways, in less time than it takes you to read this sentence. The shaking lasted around 65 seconds. That doesn't sound like much. Sit and count to 65 right now. Then imagine the floor beneath you, violently rolling for that entire duration. Buildings in the affected zone, where they existed at all, were severely damaged. Stone structures crumbled. The ground cracked open in patterns visible for kilometers. Here's a detail that almost never makes it into the standard descriptions. 2 lakes in the region disappeared. The ground subsided enough in places to drain entire bodies of water. That's the kind of geological violence we're talking about. Not just shaking, rearranging, reshaping the surface itself. But because this happened in such a remote part of the world, the documentation was sparse. Russian and Chinese observers recorded the seismic waves on distant instruments. A handful of expedition reports captured fragments of the damage, but there were no photographers walking the rupture line the next morning. No newsreel cameras, no global headlines. The event existed in the ground itself far more clearly than it ever existed in the human record. And if the story had ended there, it would already be one of the most significant strike-slip events of the 20th century. A magnitude 8 in a wildly understudied corner of Asia. But the story didn't end there. 14 days later, the same fault system did something so rare, so geometrically extreme, that it has remained one of the most studied and most argued about earthquake sequences in the entire scientific literature. On July 23, 1905, just 2 weeks after the Tsetserleg quake, the Bolnay Fault unzipped. And when I say unzipped, I mean it almost literally. The magnitude has been estimated at somewhere between 8.3 and 8.4. The total surface rupture extended for roughly 455 kilometers. Not one fault, 3. The Bolnay Fault itself, plus 2 connected structures called the Teregtian and Dungan faults, broke as a single linked system. The rupture propagated bilaterally, meaning it tore both eastward and westward from the initiation point at the same time, ripping open the Earth in 2 directions simultaneously. The offsets were staggering. Horizontal displacements reached up to 11 meters in places. Vertical offsets reached up to 9 meters. Picture 2 kilometers of road. Now, picture the entire road on one side of the fault sliding sideways the length of a school bus, while parts of it also lurch upward by the height of a 3-story building. In one event. In one continuous tearing of the crust that lasted roughly 115 seconds. To put that in perspective, the 1906 San Francisco earthquake had a surface rupture of around 477 kilometers and offsets that maxed out around 6 meters. The Bolnay rupture was comparable in length, but with offsets nearly twice as large in some places. By certain measures, this was one of the largest continental strike-slip earthquakes ever recorded by modern seismology. And it happened 14 days after another magnitude 8 on the same connected fault system. That's what makes this sequence so extraordinary. Not the size of either individual event, although both are remarkable. The pairing. 2 great earthquakes in the same network, separated by less than half a month. That kind of doublet is almost vanishingly rare in the modern instrumental record. The question every seismologist who studies this region eventually has to confront is the obvious one. Was the second earthquake triggered by the first? And if so, how? Because the distance between the 2 ruptures is far too large for the kind of immediate dynamic triggering you sometimes see when one quake's seismic waves shake another fault loose. Something else had to be going on. Something slower. Something subtler. Something that operated across days and across hundreds of kilometers. The real mystery isn't the size of the 1905 earthquakes. The real mystery is why they happened back to back, on the same system, at all. There are other examples in the modern record of earthquake sequences, where one event seems to nudge another into action. The 1992 Landers earthquake in California was followed 3 hours later by the Big Bear quake, about 40 kilometers away. The Christchurch sequence in New Zealand, from 2010 to 2011, involved multiple damaging quakes over many months along interconnected faults. These cases are well documented and well studied. But there's a critical difference. The Mongolian doublet of 1905 involved two events that were each roughly equivalent in magnitude to the largest earthquakes any of those other sequences ever produced. We're not talking about a magnitude 7 followed by a magnitude 6 aftershock. We're talking about a magnitude 8 followed 2 weeks later by a magnitude 8.3 or 4. That's like the entire San Andreas going off, and then the Hayward Fault going off 2 weeks later as a slightly bigger event. To understand how that's even physically possible, you have to wrap your head around something called post-seismic stress transfer. When a major fault ruptures, it doesn't just release stress, it also redistributes it. The crust around the rupture rearranges itself in subtle ways for years and even decades afterward. Some areas lose stress, other areas gain it. Faults that were sitting comfortably below their failure threshold can suddenly find themselves loaded much closer to the breaking point. Models developed by researchers like Jean Chéry in 2001 and Fred Politz in 2003 have shown how stress transfer can theoretically push adjacent faults toward rupture over time scales, ranging from seconds to centuries. It's not magic. It's not telepathy. It's the slow, viscous response of the lower crust and upper mantle adjusting to a sudden change in the loading conditions above. What this means is that earthquakes can trigger other earthquakes across both space and time in ways that don't require the two events to be touching, and don't require them to happen within the same news cycle. A great quake can quietly load a neighboring fault, and that neighbor might break minutes later, or weeks later, or decades later, or never at all. In the case of 1905, the 2-week gap between Setzerleg and Bolnay falls right in the window where post-seismic stress transfer becomes physically plausible as a triggering mechanism. It's not proven, it's not universally accepted, but it's coherent with what we know about how the crust behaves after a major rupture. And if that mechanism really did operate in 1905, then the implications get much more uncomfortable. Because if stress transfer triggered a second magnitude, 8 in 14 days, what's to say it stopped there? Here's where the story enters territory that makes some seismologists shift in their chairs. Because once you accept that one great earthquake might have loaded another within 14 days, the natural follow-up question is whether the same process could continue across longer timescales, decades, generations, whole human lifetimes. Some researchers have argued that the seismic activity in Central Asia throughout the 20th century may not be a series of independent events, but rather a slow-motion cascade. A multi-decade conversation between connected fault systems, each rupture quietly reshuffling the stress and setting up the next. Consider the 1931 Fuyun earthquake in northwestern China. Magnitude estimated around 8. Massive surface rupture on a fault system that, while not directly continuous with Bolnay, sits within the same broader stress regime driven by the India-Eurasia collision, 26 years after Bolnay, and then in 1957, the Gobi Alai earthquake, which we'll get to in a moment. Roughly 50 years after Bolnay, on a fault system that some researchers have linked to long-term stress redistribution from the earlier events. Now, I want to be careful here. This cascade hypothesis is not universally accepted. Many seismologists view these as essentially independent events that happen to share a tectonic neighborhood. The error bars on long-term stress transfer modeling are enormous. The data we have for early 20th century earthquakes, especially in regions like Mongolia and Western China, is patchy at best. Drawing tidy causal lines between events separated by decades and thousands of kilometers requires more confidence than the evidence usually supports. But the hypothesis exists. It's published. It's debated. And it raises a question that I think is genuinely worth sitting with. What if Earth systems don't operate on human timescales? What if the great earthquakes of Central Asia in the 20th century weren't a series of unrelated accidents, but the visible peaks of an underlying process that has been unfolding, slowly and patiently, for over 100 years? Half a century after Bolnay, the system moved again. And when it did, it left behind something so well preserved, so geologically pristine, that it has become a reference point for the entire science of paleoseismology. On December 4th, 1957, in the Gobi Alai region of southern Mongolia, the Earth let go again. The magnitude has been estimated between 7.8 and 8.1, depending on which study you read and which seismograph network you trust. By any measure, it was one of the largest earthquakes of the 20th century anywhere on the planet. But the magnitude isn't even the most interesting part of the Gobi Alai event. What makes this earthquake genuinely unusual is its geometry. Most great earthquakes are dominated by one type of motion. Either strike slip, where the crust slides horizontally, or thrust faulting, where one block rides up over another, or normal faulting, where the crust pulls apart. Gobi Alai did all of it. It was a complex multi-mode rupture, with both strike slip and thrust components active during the same event. The strike slip portion of the rupture extended roughly 250 to 300 kilometers along what's called the bogged fault. The thrust portion added another 100 kilometers or so of crustal shortening, where blocks of earth literally rode up over each other. Maximum offsets reached around 8 to 9 meters horizontally. The shaking unleashed aftershocks, reaching up to magnitude 6.8 in the months that followed, themselves powerful earthquakes that on any other day would be major news. The death toll was somewhere around 30 people. 30. From an earthquake that, by raw seismic energy, rivals some of the deadliest disasters in human history. Once again, this was the gift and the curse of remoteness. The Gobi Desert in 1957 was one of the most isolated regions on Earth. There were almost no permanent settlements in the rupture zone. There were almost no buildings to collapse. There were almost no people to be killed. A magnitude 8 earthquake released in a populated region would have killed tens or hundreds of thousands of people. Released in the Gobi, it killed 30. The same physical event with vastly different human consequences. And because almost no one was there to witness it, the earthquake left behind something almost no other event of its size has ever left behind. A near perfectly preserved scar. If you want to understand why the Gobi Alai earthquake matters far beyond Mongolia, you have to understand what happens to most fault scars after a great earthquake. They get eroded. They get plowed under. They get built over. Rain washes the offsets away. Vegetation reclaims the scarp. Within a few decades, even a massive surface rupture can become almost invisible to the casual eye. The Gobi Desert is one of the most arid environments on Earth. Annual rainfall in some parts of the rupture zone is measured in single-digit centimeters. There's almost no vegetation. There are almost no rivers to cut new channels through old ones. And there's almost no human activity to disturb the surface. Which means the 1957 rupture has been preserved in almost pristine condition for nearly 7 decades. You can fly a drone over parts of the bogged fault today and see with your own eyes the exact line where the Earth tore itself open in 1957. The scarp is still there. The horizontal offsets are still measurable. Streams that were displaced by the rupture still show the bend. It's like looking at a freshly opened wound that the planet refused to close. This has made the Gobi Alai rupture an absolute treasure for the science of paleoseismology. Researchers use it as a calibration reference, comparing modern measurements of the scarp to what we know about the earthquake that created it, and using that comparison to interpret much older, more weathered fault scarps elsewhere in the world. If you want to understand what a great earthquake actually does to the surface of the Earth, you go to the Gobi Alai rupture, There aren't many other places where the evidence is so clean, and there's something almost uncomfortable about standing next to that scarp. Imagine looking at a continuous line in the dirt that stretches to the horizon, knowing that line was created in a single afternoon, in a single moment, by forces that lifted and shifted entire mountains. If this fault system can preserve its past so clearly, the obvious follow-up question is what else it might be preserving. What other ruptures lie buried in the Mongolian crust, written in offsets that no one has yet mapped? What other secrets is the system holding on to? This is where the cascade hypothesis comes back around. Because once you have a magnitude 8 in 1905, followed by another magnitude 8 a few weeks later, followed by a magnitude 8 in 1931, followed by a magnitude 8 in 1957, all in the same broad tectonic system, the human pattern recognition instinct starts firing on all cylinders. Was the 1957 Gobi Alai earthquake somehow triggered across half a century by the 1905 Bolnay rupture? The supporting argument goes like this. Long-term stress transfer models do show that a great earthquake can alter the stress field in surrounding regions for many decades, particularly in the lower crust, where viscous flow operates on much slower timescales than the brittle upper crust. Some studies have argued that the post-Bolnay stress evolution would, over time, have loaded portions of the Mongolian fault network in ways that brought the bogged fault closer to failure. The counter-arguments are also strong. The distance between Bolnay and Gobi Alai is several hundred kilometers. The intervening crust is complex. The faults involved have different orientations and different mechanical properties. Linking them through a clean stress transfer chain requires assumptions that are difficult to verify, and there are plenty of alternative explanations, including the simple possibility that this region is just so seismically active, on its own, that great earthquakes happen here regularly, even without any cross-fault triggering. The honest answer is that the cascade hypothesis is plausible, but unconfirmed. It might be right. It might be wrong. It might be partially right. Causality in earthquake science is rarely as clean as causality in a controlled laboratory experiment, because we can't run the experiment twice. We have one Earth, one history, and one chain of events to interpret. What I'll say is this. The temptation to draw confident lines between distant earthquakes is something to resist. But so is the opposite temptation, the urge to dismiss any possible connection just because the data is messy. The truth, as is so often the case in geophysics, sits in a fog somewhere between the two extremes. After 1957, the Bolnay-Khangai-Sayan system and the broader Mongolian seismic zone connected to it went quiet, not silent. Smaller earthquakes continued to occur. The crust kept fidgeting in its usual way. But there were no more magnitude 8 events, no more great ruptures, no more fault scars stretching to the horizon. That quiet has now lasted 69 years, going on 70. You might be tempted to read that as good news. The system is calm, the pressure has been released, the Earth is taking a break. But here's the paradox that lies at the absolute center of how earthquake science actually works. Quiet is not the same as inactive. A fault that hasn't ruptured in decades is not a fault that has nothing to give. It is, in many cases, exactly the opposite. It's a fault that has been quietly accumulating strain the entire time, loading itself toward a threshold that no one has been measuring closely. The crust on either side of these fault systems is still moving. The India-Eurasia collision hasn't stopped. The continental escape tectonics that drives this whole region hasn't paused for a coffee break. Every year, the strain continues to accumulate. Every year, the elastic stress stored in the rocks gets a tiny bit higher. So if the system has been quiet for 69 years, and the engine that loads it is still running, The natural question becomes how long this period of quiet is supposed to last. Is 69 years a long time in the lifespan of a fault system like this? Or is it almost nothing? Is the system overdue for another great earthquake? Or is it nowhere near ready? To answer that, we have to talk about what the recurrence interval of this system actually looks like. And that's where most of the popular narratives about earthquake risk fall completely apart. The Bolnay-Khangai-Sayan system has a long-term slip rate of roughly 3 millimeters per year. That's the average rate at which the two sides of the fault network are moving past each other when you smooth out all the bumps and pauses and sudden jumps. 3 millimeters a year. That's about the thickness of 2 stacked credit cards. That's how fast this enormous fault system is grinding away. Now, when a great earthquake hits this system, the typical offset in a single event is somewhere between 8 and 11 meters. That's the amount of slip that gets released in one rupture. So if you want to know roughly how long it takes to accumulate enough strain to produce another great earthquake, the math is brutally simple. Take the offset, divide by the slip rate, and you get the recurrence interval. 8 meters divided by 3 millimeters per year. 11 meters divided by 3 millimeters per year. The answer comes out to somewhere between 2,600 and 3,600 years. Some estimates push it as high as 4,000 years, depending on the segment. Sit with that number for a moment. The natural recurrence interval for great earthquakes on this fault system is on the order of 2,000 to 4,000 years. That's longer than the entire span of recorded human history in most places. That's longer than the time since the construction of the Egyptian pyramids. Compared to that timescale, the 69 years of quiet since 1957 isn't even a rounding error. It's a fraction of a percent of the cycle. The system has barely begun to recharge. But here's the trap. Earthquake recurrence is not a clock. It is not regular. The crust does not produce a great earthquake every 2,700 years, like a Swiss watch. The numbers we calculate from slip rates are long-term averages. Actual recurrence in any given segment can be much shorter or much longer than the average. Faults can cluster events in close succession, then go silent for unusually long periods. The math gives you an order of magnitude, not a date. So when someone asks whether this fault system is overdue for another great earthquake, the honest answer is that the question itself is poorly posed. There is no schedule. There is no due date. There is only a slow accumulation of strain and a probability distribution that nobody can tighten without far more data than we currently have. Let me put a specific number on this so you can see exactly how distorting human timescales can be when applied to fault systems. If you measure from 1905, when the Bolnay earthquake unleashed 11 meters of offset in a single event, the time elapsed is 121 years. From 1957, when Gobi Alai released its own 8 to 9 meters of slip, the time elapsed is 69 years. Compare those numbers to the natural recurrence interval of 2,000 to 4,000 years. We are at roughly 3 to 6% of the cycle. 3 to 6%. If you imagine the seismic cycle as a single year, with January 1st being the day after a great earthquake, and December 31st being the day before the next one, then today, on this segment of the system, would be somewhere around January 8th or January 12th, maybe January 15th at the outside. We are not late. We are not on the verge. We are barely out of the first week. This is the part of earthquake science that almost never makes it into popular media coverage, because it doesn't fit the narrative most stories want to tell. The overdue earthquake framing is dramatic. It's easy to digest. It implies a countdown clock that we can almost watch ticking, and it's almost completely wrong, especially for fault systems with long recurrence intervals like this one. The truth is that the Bolnay-Khangai-Sayan system, after the 1905 and 1957 ruptures, is essentially in its early youth as far as the seismic cycle is concerned. The strain accumulated in the past century is real, but it's a small fraction of what would be needed to produce another great earthquake on the same segments. Now, that's not the whole story. Different parts of the network are at different points in their individual cycles. Some segments haven't ruptured in the modern record at all, which means they could theoretically be much closer to failure than the segments that broke in the 20th century. The system is not uniform. The clock is not single. It's a network of overlapping cycles, each running on its own schedule, each loading the others as they go. Which brings us to the real question. If the system isn't overdue, why are we even paying attention to a small cluster of quakes in 2026? Do small earthquakes signal the approach of large ones? This is one of the most studied, most argued about questions in all of earthquake science, and the honest answer is that we don't know. The relationship between small foreshocks and large main shocks is messy at best. In some cases, large earthquakes have been preceded by clusters of smaller events that, in retrospect, look like clear precursors. In other cases, those same patterns have appeared and led to absolutely nothing. And in still other cases, large earthquakes have struck with no detectable warning at all. The data we have is too sparse. The patterns we think we see are often products of pattern recognition rather than genuine physical signals. The human brain is an extraordinary machine for finding meaning in noise, and seismic data is exactly the kind of noisy signal where the brain tends to overperform. There have been attempts to develop earthquake forecasting based on small event clustering. Some of these approaches have produced statistically interesting results in retrospective analyses. None of them have produced operational forecasts that work reliably enough to issue public warnings. The field has been chasing this question for over 100 years, and we are not significantly closer to an answer today than we were a generation ago. So when I tell you that 3 quakes hit the Bolnay-Khangai-Sayan system in 24 hours, and you feel a small, involuntary jolt of, "Is something coming?" you should know that your reaction is normal, and also that there is no rigorous scientific basis for it. The cluster might mean something. The cluster might mean nothing. There is no current method to tell the difference in real time. What we can say is that the cluster fits a broader picture. It happened on a system that has produced great earthquakes in the past. It happened in a region that is being actively loaded by tectonic forces that haven't stopped. It happened in a part of the world where monitoring is sparse, and where some of the most extraordinary seismic events in modern history have unfolded with very little warning. That's not a prediction. That's just context. And context, in this kind of story, is everything. I want to come back to the idea I introduced at the very beginning, because it's the single most important concept for understanding why this story matters. The Bolnay-Khangai-Sayan system is not a fault. It is a network, and earthquake networks behave differently from individual faults. When you study a single fault, you can, with enough effort, build a reasonable picture of its loading rate, its slip history, and its recurrence pattern. You can put error bars on your estimates. You can issue probability statements that, while uncertain, are at least mathematically tractable. When you study a network, all of those tools start to break down. Faults interact across distance. Ruptures can jump from one segment to another in ways that are hard to predict. Stress fields overlap. Post-seismic relaxation in one part of the network changes loading conditions in another part. The behavior of the system is emergent. It depends on the configuration of the entire network, not just the properties of any one piece. This is why the great Mongolian earthquakes of the 20th century were so unusual, and why they remain so important to study. They didn't behave like isolated events. They behaved like coordinated expressions of a much larger system. The 1905 doublet, with 2 magnitude 8 events on linked faults 14 days apart, is exactly the kind of behavior that you cannot understand by treating either fault in isolation. If the system is connected at the scale of 1,500 kilometers, then the relevant unit of analysis is the whole network. And if the relevant unit is the whole network, then the question of where the next great earthquake might originate becomes much harder to bound. It also raises an unsettling possibility. If this fault network is connected to itself across 1,500 kilometers, what other systems might it be connected to? Where do the influences of one stress field end and another begin? Are the boundaries we draw on tectonic maps real, or are they conveniences we invented because the actual continuous reality is too complex to map? These aren't rhetorical questions. They're questions that matter for hazard assessment everywhere on Earth, and in Central Asia, they remain wide open. Let's allow ourselves for a moment to take the cascade hypothesis seriously, not as a confirmed truth, but as a framework worth thinking through. If the great earthquakes of 1905, 1931, and 1957 were genuinely linked through long-term stress transfer, then the cascade did not necessarily end in 1957. Stress redistribution operates on timescales that can extend for many decades. The Earth doesn't reach a new equilibrium overnight after a great earthquake. The crust, the mantle, the deep, viscous layers all keep adjusting for 50, or 100, or 200 years. If that adjustment is still ongoing, then the question becomes whether the Central Asian crust, today, in 2026, is still in a state of slow post-cascade rebalancing. And if it is, then small clusters of moderate earthquakes in different parts of the network might not be random. They might be the visible surface expressions of a much deeper, much slower process that is still working itself out. Other moderate earthquakes have occurred across the broader region in recent decades. The Tuva region, Western Mongolia, the Sayan Ranges, northern China. None of them individually has been particularly remarkable. Taken together, they form a pattern of low-level activity that is consistent with an active, loaded, but currently subcritical fault network. I want to emphasize again that there is no unified scientific model that proves any of this. The cascade hypothesis is a way of thinking about the data, not a confirmed mechanism. Many seismologists are skeptical, and their skepticism is well-founded. The signal-to-noise ratio in long-term stress transfer is low. The error bars are enormous. The simplest interpretation of the recent activity is that this is just a tectonically busy region, behaving the way tectonically busy regions always behave. But the question is open, genuinely open. And open questions in geophysics are the ones worth paying attention to. Here's something that might surprise you. If a great earthquake started building up in Central Asia today, slowly accumulating strain, generating subtle precursors that we know how to detect in principle, we might not see it coming. The reason is straightforward. Mongolia, southern Siberia, and northwestern China are among the most under-monitored, seismically active regions on Earth. The number of high-quality seismometers is small. The coverage is sparse. The Global Positioning System network, which is critical for measuring slow strain accumulation across faults, has comparatively few stations in this part of the world. Compare that to Japan, where every kilometer of crust seems to have its own dedicated instrument, or California, where the dense network can detect tiny tremors and slow slip events across the entire San Andreas system. Those regions have decades of investment, sophisticated infrastructure, and continuous data streams that allow seismologists to watch the crust breathe in near real time. Mongolia does not have that. There are excellent regional networks. There are dedicated researchers doing remarkable work with limited resources, but the density of coverage is nowhere near what it would take to detect the kinds of subtle precursory signals that have, in some other places, preceded great earthquakes. What this means is that even if the science of earthquake forecasting were better than it is, our ability to apply that science in Central Asia would still be limited by the simple fact that we are not watching closely enough. precursors might be happening. Slow slip events might be unfolding. Stress changes might be accumulating in measurable ways. We just don't have the eyes on the ground to see them. This is one of the quiet tragedies of global earthquake science. Some of the most important fault systems on Earth are in some of the least monitored regions. The places where the next great rupture might originate are not necessarily the places where we have the best chance of seeing it coming. And so we end up in a position where the most we can really say, even with the best science we have, is that this system is real. This system is loaded. This system has produced great earthquakes before, and we are watching it through a small and partial window. Let me tell you about something that happened just before the 2011 Tohoku earthquake in Japan. In the weeks leading up to that magnitude 9 event, which devastated the Pacific coast of Japan and triggered the Fukushima nuclear disaster, scientists later discovered that a slow slip event had been unfolding along the subduction zone. A slow slip event is a kind of silent earthquake. The fault is moving, but it's moving so slowly that it doesn't generate seismic waves you can feel. It generates measurable ground motion only in the precise data streams of GPS networks and high-quality strain meters. The pre-Tohoku slow slip was only recognized in retrospect. Nobody saw it as a warning at the time. But after the earthquake, when researchers went back and looked at the data, they saw it clearly. The crust had been quietly creeping in the weeks before the rupture. The fault had been giving signals. They were just signals nobody knew how to read in the moment. This raised a deeply uncomfortable question for earthquake science. How often do great earthquakes have slow slip precursors? How often are they happening, right now, on faults around the world, and being missed because the monitoring is not dense enough or the analysis tools are not sensitive enough? We don't know. The honest scientific answer is that we don't know. Slow slip events have been documented in detail in subduction zones with dense monitoring networks. They've been observed less frequently on continental strike slip faults, partly because those faults are usually less well instrumented. The Bolnay-Khangai-Sayan system, with its sparse monitoring and its history of great strike slip ruptures, is exactly the kind of place where slow slip precursors could potentially occur and remain almost completely undetected. Could a slow slip event be happening on a Mongolian fault right now, quietly preceding a great earthquake that is years or decades away? The truthful answer is that nothing we currently observe can rule that out. The truthful answer is also that nothing we currently observe suggests it is happening. We are, in the most literal sense, in the dark. This is the absolute frontier of earthquake science. Not what we know, but what we can't yet measure. And in regions like this one, that frontier is unusually wide. Let's go back, one last time, to 4:23 in the morning on April 26th, 2026. A magnitude 5.9 earthquake in Western Mongolia. Two smaller quakes in the preceding day. Pager green. Almost no damage. Almost no casualties. Almost no global news coverage. By the standard metrics of disaster reporting, a non-event. But that's the trap I want you to step out of, just for a moment. Because the standard metrics of disaster reporting are exactly what cause the most dangerous fault systems on Earth to remain invisible to the public imagination. The metrics measure consequences. They don't measure potential. They measure damage to cities. They don't measure stress on faults that pass through almost no cities at all. The quakes of April 26th weren't a warning. They weren't unusual in any statistically meaningful sense. They weren't proof of anything coming. If you take nothing else from this entire story, take that. There is no reason to walk away from this video thinking that a magnitude 8 earthquake is about to hit Mongolia. The science does not support that claim, and I won't pretend that it does. But the quakes were also not nothing. They illuminated something. They drew a line through the surface of the Earth that pointed to a system most people had no idea existed. A system 1,500 kilometers long, a system that has produced 2 magnitude 8 earthquakes within 14 days. A system that ripped open the largest preserved earthquake scar on the planet. A system that is still loaded, still active, still being driven by the same continental collision that has shaped Asia for 50 million years. And a system that almost no one outside specialist seismology has ever heard of. That, in the end, is the real story. Not the 3 small quakes, not the magnitudes or the dates or the depths. The fact that the most consequential geological structures in our world are not always the famous ones. Some of them are quiet. Some of them are remote. Some of them have been waiting, patiently, while the rest of us kept our attention pointed somewhere else. The most dangerous fault isn't the one that moves the most. It's the one no one is paying attention to.